this example, I have a large flywheel that's got a fixed center of rotation at the middle. It's being accelerated from rest by a 15 kilogram mass that is falling. And I want to know the velocity of the mass after it has fallen 2 meters, starting from rest. I'm also given that this flywheel has a mass moment of inertia of 3 kilogram meters squared. I don't know the mass, but it's okay, I just need the mass moment of inertia. And I'm given the radius of this flywheel is 0.3 meters. Looking at this problem, I have masses, distances, and velocities, so I'm immediately thinking conservation of energy or the work energy principle. And I'm going to go ahead and use conservation of energy here, but it works just as well to use the work energy principle. So using conservation of energy, which I'm just going to approximate as COE, conservation of energy, my governing equation is my initial kinetic energy plus the sum of the potential energy plus the sum of all the non-conserved work from 1 to 2 is equal to the final kinetic energy plus the final potential energy. And so now I'm going to step through this and see what I have. So initially it says it starts at rest, which means there's no initial kinetic energy. I don't need to worry about that. Initial potential energy, this could either be elastic potential energy from springs or other deformed objects, which I don't have here, so I don't have to worry about that, or from gravitational potential energy. And because this 15 kilogram mass is falling, I'm going to have initial potential energy from this mass. So I'm going to have mgh. And that's all my potential energies. Non-conserved work now. I am going to consider this as one system instead of as a flywheel and as a falling mass. If I considered it as 2 separate systems, so if I was looking just at the falling mass, I would have to look at the work done by tension here. But because I look at the thing, I'm going to look at the system as a whole, the work done by tensions on these 2 will cancel out, and I don't need to worry about it. If I do that, then there's no non-conserved work. All right, so that's my whole left side. On my right side now, final kinetic energy. I know that this mass is going to be moving. That's what it's asking me to find. So I'm going to have a 1/2 mv squared. And I'm also going to have a kinetic energy of this flywheel moving. It's going to have rotational kinetic energy. So the rotational kinetic energy is 1/2 I omega squared. So I'll have 2 kinetic energy terms, one for each of these objects. And then potential energy, again, there's no springs, and my mass now has fallen as far as it goes, so I don't think there's any final potential energy. So here's my governing equation. And I think I know just about everything here to be able to solve. I know my mass is 15 kilograms, so that's good. I know gravity in the metric system will be 9.81 meters per second squared, assuming we're on Earth. And my H1 was given to me as 2 meters. And then my mass, again, is 15 kilograms, and I'm trying to solve for that final velocity. And my mass moment of inertia was given to me as 3 kilogram meters squared, and my final angular velocity. Okay, so now it turns out there's 2 unknowns in this equation. There's the velocity and the angular velocity. But this is linked motion. And so we can recall that the angular velocity of my flywheel here will equal the velocity at the edge divided by the radius. Or we could say something like the velocity at the edge is the angular velocity times the radius. So I'm going to go ahead and use this to substitute in for my angular velocity to be able to have just velocity in that final equation because I know my radius. So here, if I plug that in here, now I'll have V over R, and my R is 0.3 meters. So if I do that substitution, I'll have an equation that looks like this. And I have just my unknown final velocity now, and so I can solve for that. My final velocity is 3.49 meters per second. I just jumped straight to meters per second, but let's go ahead and check our units as well while we're here. So on the left side, I have kilogram meter squared per second squared. And then on the right side here, I have kilograms. So this will be meters per second squared, then will give me meters squared second squared, so that will work. And here I have kilogram meter squared divided by meter squared, so that will give me just 1 over second squared. Or that will give me here, let's see, kilogram meters squared divided by meters squared gives me a velocity. Right, but then I need meters per second squared to get this to all. We still need a meter squared and a second squared because these meters squared down cancel out, so it's still meters per second over there. Whew, glad that worked out. So final answer, 3.49 meters per second. And if you are curious and you go back one step, you'll see that actually the majority of the kinetic energy here is in the flywheel and not in the falling mass. So this has some kinetic energy, the falling mass. The majority of the kinetic energy is in this flywheel. So flywheels are big rotating things that we use their kinetic energy to store energy, usually for long periods of time, which is nice.